Hello everyone, I am Brigurish Mishra, a PhD student at IIT Bombay, and this is the online session of elements of solar energy conversion. This is week 12. This is the last session, okay, of this course. So in this session, we will solve some problems related to uh, carrier injection, dark current, and forward bias, reverse bias related problems. Okay, so first of all, a brief overview whatever has been discussed in the lecture. Okay, I am covering lecture 33 and lecture 34. Lecture 35 will be covered by another TA, Mr. Pawan. Okay, so in lecture 33 and 34 we talked about the forward bias and reverse bias current. So in forward bias, only uh, when external voltage applied, the the potential barrier between the p-n junction reduces, and thus electron can or you can say the charge carriers can move from one side to another side due to diffusion, or due to the difference between the concentration. Okay, so that is why in forward bias, uh, due to diffusion, the current increases. However, the the drift current remains same. Okay, so and then we have also seen the number of charge carriers moved from one position to another, from one side to another side due to this biasing. And then we also saw that at at depletion region, the the current density is constant. Okay, so current density doesn't have any effect of external biasing, okay, in the depletion region. And so yeah, I'll just write couple of formulas, okay, then we will move on to the problems. So for forward bias, the total current can be calculated as I naught exponential of minus q va by kt. Okay, here va is the externally applied voltage. Okay, so there will be two voltages. One is the v naught when there is this equilibrium. Okay, and the other one is va when this va is the externally applied voltage. Okay, and then in the case of reverse bias, the total current is qva by kt minus 1. Okay, so and then we have also saw that increase in minority carrier concentration at the edge of SCR. Okay, so it is delta Pn Pn naught. This is Pn naught is the carrier concentration at equilibrium. Okay, so it is e to the power q Va by kt minus 1. This is for holes in n side. Okay, and now electrons in p side minus xp. This is xn xp are nothing but, so suppose this is my depletion region. Okay, so this is minus xp and this position is xn. Okay, and somewhere here is the origin. So this w is xn plus xp. This is the width of the the depletion region, or SCR you can say. So delta NP is NP naught. This is again the carrier concentration of electron at p side at equilibrium, e to the power QVA by KT minus 1, and this is for electrons. Okay, so and we also saw that how so there is the the diffusion length. Okay, diffusion length for minority carrier, diffusion length for minority carrier, this is ln equals to dn tau n. This is dn is the diffusion coefficient and tau n is the lifetime. Okay, to the power half. So this we can these so now these we can write in terms of this function x. Okay, because as x changes, the concentration change in concentration or in injection of carrier concentration changes, either decreases or increases, that we will see. So that can be written as, so for example, delta np, and now this is a function of x, so it is np naught e to the power qv by kt minus 1 e to the power minus x by ln. Okay, this ln is the this diffusion length. So and in this way we can calculate the diffusion current. Okay, for example, or I can write the total current, not the individual. So I can write J total equals to Q dp by lp pn naught plus dn by ln np naught e to the power qv by kt minus 1. Okay, and we can also write, so here J naught, that is the saturation current density, can be written as uh, sorry, I naught, saturation current, can be, or I can say, yeah, saturation. So this portion is the J naught. Okay, so I can write the dark current. Dark current is nothing but I equals to I naught e to the power qv by kt minus 1, and this I naught is nothing but uh, j naught into a, where a is the cross section area. Okay, so we will use these formulas to solve the question. So these are just overview of the main formulas which is required to solve the questions. So the first question is calculate the reverse saturation current density of a PN junction diode. Okay, so we have to calculate the saturation current density. That means we need to calculate J naught. Okay, saturation current density of PN junction diode. Doping level at the P side and N side of the silicon PN junction are 1 into 10 to the power 14 boron atoms per centimeter cube and 1 into 10 to the power 18 phosphorus atoms per centimeter cube. These BP are the dopants. Okay, respectively. The diffusion length of electrons and holes are 40 micron and 10 micron. Uh, sorry, this is 100 micron, not 10 micron, respectively. And the diffusion coefficient of electrons and holes are 35 centimeters square per second and 10 centimeters square per second, respectively. Okay, so we can calculate. So 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 the formula is reverse saturation current J naught equals to Q, which is the charge of an electron, or the charge dN by ln, and P naught plus dP by Lp Pn naught. So we have given ln is 40 micrometer, Lp 100 micrometer, Dn 35 centimeter square per second, dP 10 centimeter square per second, np naught equals to 2.25 into 10 to the power 6 atoms per centimeter cube. P naught equals to 2.25 into 10 to the power 2 atoms per centimeter cube. Okay, so all the values has been given. So now putting all the values here, and Q is 1.6 into 10 minus 19, so Dn is 35 by 40 into 2.25 into 10 to the power 6 plus dP 10 by Lp 100, sorry, Pn naught is 2.25 into 10 to the power 2. Now if you compare these two, so this is significantly small. Okay, significantly small compared to the first one, so we can neglect this. So J naught can be written as 1.6 into 10 to the power minus 19 into 35 by 40 into 2.25 into 10 to the power 6. If you solve this, you will find 3.15 into 10 to the power 10 ampere, minus 10, sorry, ampere per centimeter square. Okay, so this is the saturation current, 3.15 into 10 to the power minus 10 ampere per centimeter square. Okay, so we just put all the values in the formula. Okay, we haven't done much. It's just a simple formula based question. Okay, here we just need to know which value belongs to uh, which parameter, which variable. Okay, so you should know that here this doping level at p side, that is 1 into 10 by 14 boron atoms per centimeter cube, is nothing but the uh, np. Okay, and all the other values. Sorry, I think I have missed something here. I have taken different values. uh, yeah, it's both are 2.25 into 10 to the power 6, and this one is uh, 2.25 into 10 to the power 2. Okay, the values I have written wrong. Okay, so question 2, use data given in the Q1 and so whatever the data given in Q1, and calculate dark current density at room temperature with applied voltage 0.5 volt. Okay, so dark current can be calculated as, so dark current density, this is the dark current, so it can be written as J equals to J naught. Okay, so it is J equals to J naught e to the power qv by kt minus 1. So we have given that V equals to 0.5 volt and temperature is room temperature, so we can take 27 degrees centigrade. Okay, that means 300 Kelvin. So here we can calculate uh, QV by KT. This comes around 19, I guess. Yeah, it's 19.32. So it's 19.32. So so and J naught we already got from here. So this is 3.15 into 10 to the power minus 10 into e to the power QV by KT. So this is e to the power 19.32 minus 1. Okay, so this, and this is unit is ampere per centimeter square since it is current density. So now this e to the power 19.32 minus 1, this is approximately 2.47 into 10 to the power 8. Okay, so the dark current is J equals to 7.78 into 10 to the power minus 2 ampere per centimeter square, or you can write it, it's 0.078 ampere per centimeter square. Okay, so this is the dark current density. This is dark current density. So now the third question is determine the value of dark current in the limiting case V equals to 0. So we know the formula I equals to I naught e to the power QV by KT minus 1. Okay, so this is a very straightforward question. So when the limiting case is when V equal to 0. Okay, so when V tends to 0, this QV by KT is also tends to 0, and in that case this e to the power QV by KT tends to 1. Okay, so it's a straightforward, simply I equals to I naught 1 minus 1, and thus I also tends to 0. Okay, so when there is no voltage, then dark current also 0. Okay, but dark current 0, that doesn't mean that there won't be any saturation current. Saturation current will be there. Okay, just when V equals to 0, there won't be any dark current present. Okay, so this is the last question. So draw the profile of the injected minority carrier at the P side of the junction as a function of applied voltage of 0.5 volt and for the following diffusion lengths: 10 micron, 50 micron and 200 micron. Okay, so we need to plot this the profile of the injected minority carrier with respect to the uh, x. Okay, this axis, the this x varies, like I can say from one region to another region. So I'm assuming that uh, that so considering this, so suppose this is the minority at p side, that means electrons, so it goes from n side, so I'm considering from here. Okay, so I'll start from this, that is whatever at this side, and then whatever will go here. So this is in x direction. Okay, so let's see. So first of all, uh, so why this injection happens? So due to the forward biasing, carriers are injected from their majority side to the minority side. Okay, the number of injected carriers is affected by, so the number of injected carriers is affected by the applied bias voltage and the concentration profile of the injected minority carriers. Okay, as they travel away from the depletion region edge, and this depends on the minority carrier diffusion path, this path. Okay, this path from this side to this side, that also depends. So uh, so the profile of minority carrier is given as np of x equals to np naught plus delta n, which is equals to np naught plus np naught into e to the power qv by kt minus 1 e to the power minus x by ln. So here we need to plot this change. Okay, this delta n, which is equals to np naught e to the power qv by kt minus 1 e to the power minus x by ln. Okay, so first let's calculate the quantities which we can easily get. So again, this is so voltage, applied voltage is 0.5, so V is given 0.5 volt, and temperature we can take room temperature, so 273 plus 27, that is 300 Kelvin. So if we solve this qv by kt, that is 1.6 into 10 to the power minus 19 into 0.5 divided by 1.38 10 to the power minus 23 into temperature, which is 300. So it uh, comes around 19 point just a minute. So yeah, it comes around 19.32. Oh, we have already calculated it in the previous question. So this e to the power 19.32 minus 1, this is 246697017.9, so we can approximate it to 2.47 into 10 to the power 8. Okay, so now delta np is np naught 2.47 into 10 to the power 8 into e to the power minus x by ln. Okay, now this np naught, so we can take from the first question np naught is 2.25 into 10 to the power 6. So we can take this value. So delta np will be 2.25 into 10 to the power 6 into 2.47 into 10 to the power 8 into e to the power minus x by ln. If you solve this, I will end up with 5.56 into 10 to the power 14 uh, into e to the power minus x by ln, and the units will be atoms per centimeter cube since this is the concentration. So let's make a table for so we have to plot for 10 micron, 50 micron and 200 micron. Okay, so let's plot it for let's calculate the values for 10 micron. Okay, so uh, so here then we need to only vary the x. Okay, so x and delta n. So suppose x, this x is in micron. Okay, so x I have taken 10, 50, 100, 150 and 200. So these five values I have taken for this. So if you calculate delta n, uh, comes 2.04 into 10 to the power 14, 3.75 into 10 to the power 12, 2.52 into 10 to the power 10, 1.70 into 10 to the power 8, 1.14 into 10 to the power 6. So these are the values. Now if you see, the difference is very large. So 6, 8, 10, 12, 14. Okay, so as x is increasing, the change in carrier concentration of electron is decreasing. So at 10 micron it has the order of 10 to 14, 10 by 14, but at 200 micron it is reduces to 10 to the power 6. So 8 order difference. Okay, so now these values are very large. So in order to plot uh, a decent graph, means like the, the difference between the points will be too large. So what we can do is we can take the log. Okay, natural log. So ln of delta n. So this I have already calculated it. 32.95, 28.95, 23.95, 18.95, and the last one is 13.95. Okay, so we have the log. So we will plot between ln delta n and x. So let's plot here. X, and this is ln delta n p. Okay, these are all delta n p. So so that this is origin 0. So let's say 50, 100, 150, 200, and here 5, 10, 15, 20, 25, 30, 35. Okay, so now 10 will come somewhere here. So at 10 micron the ln is 32.95. Okay, so somewhere here 30, somewhere here, this is the first point. At 50 it is 28.95. So at 50, 28.95 is somewhere here, a little bit more towards this. Mm, yeah, somewhere here, closer to 30. At 100 it is 23.95. At 100 it is somewhere here. Okay, at 150 it is 18.95. So 150, 18.95 is somewhere here. At 200 it is 13.95. 200, 13.95 means somewhere around here. Okay, so if you connect all the points, you will find something uh, yeah, something like this. So this is more or less a straight lines. Okay, it's a basically straight line. So this is for ln equals to 10 micron. So this is for ln equals 10 micron. We can show for one more. Okay, since we need to know how it varies when diffusion length changes. So let's calculate the values of the other uh, other diffusion length 50 micron. Okay, so when ln equals to 50 micron, delta np will be 5.56 into 10 to the power 14 into e to the power minus, so this is so uh, so it's simply 1 divided by 50, so 0.02 0.02x. Okay, so now making again this kind of chart. So x micrometer, delta np, and then ln delta np. So again we'll take the same set of x values: 10, 50, 100, 150 and 200. So delta np is, so this is 5.56, 14 into e to the power minus 0.02 into 10. So it comes 4.55 into 10 to the power 14. Okay, now for 50, it, it's 2.045 into 10 to the power 45. For 100, it's sorry, uh, 100 is 7.52 into 10 to the power 13. For 150 it is 2.768 into 10 to the power 13. And for 200 it is 1.018 into 10 to the power 13. Okay, so if you compare with this, it doesn't decrease very much. Okay, So now we calculate the logarithm of this. So ln 4.55 into 10 to the power 14. So this is 33.75. Two point zero four five. This is 32.95, and the next one is 7.52. So this is 31.95. Now the next one is 2.768. So this is 30.95, and the last one is 1.018 30. So this is 29.95. Okay, so these are it's almost a straight line. Okay, so let's plot the value. So at 10 it is 33.75. So this is, so it will be just above uh, this one. Okay, and then at 50 it is 32.95. So at 50, somewhere here, at 100 it is 31.95. So just above this here, you can say one, you can draw it with the proper scale. Okay, here I'm just doing the rough, and also please check these calculation, this especially this for 50 micron, whether it is correct or not. So for 150 it is 30.95. So again this is just here. At 200 is 29.95. So it is just here, and this one is here somewhere here. Okay, so it also follows the trend, but the reduction is not like the slope is not same as the first line. Okay, so this is for ln equals to 50 micron. Okay, in the same way you can also plot for ln equals to 200 micron. Okay, so of course it will go here. So as you can see, when the diffusion length is high at large distance, also for example in this case for 200 micron, the the concentration doesn't decrease much. Okay, so for example, if you observe all these points, so here at okay, so this is 10 micron. So at 10 micron, for both the diffusion length, the two concentrations are very close to each other. So as thickness increases, the gap between the two concentrations increases. Okay, so for 10 micron thickness, the concentration uh, decreases quickly with the increase in the length. But for 50 micron diffusion, it's not very much. Okay, the decrease is not very much, so slope is very less. So that is why at 200 also it is close to 30 for 50 micron, whereas for 10 micron it is close to 14. So the difference is lot. So I guess if you plot the same thing for 200 micron, you will probably get a flat line. Okay, or the difference will be very small. Also please remember that this is in logarithmic scale. Okay, this is not the normal or the linear scale. So if you plot in the linear scale, then of course you will observe. So there you need a lot of big big scale. Okay, because you know the the difference is very large. For example, for 10 micron it is 10 by 14, and for 200 it is 10 per 6. So the difference is large, but this is not the case for this for 50 micron diffusion. Okay, because here the for 10 micron it is 10 per 14 order of, and for 200 10 to the power 13 order. Okay, so yeah, you can plot this for 200 micron also. So yeah, that's it for this last session. So thank you very much.